So folks, previously we've looked at, well actually this is a college algebra review skill, but we want to express this function whose graph is shown here as a piecewise function. So go ahead and pause the video and give that your best shot. I think you'll find the solution somewhere else on this page, but give it a shot. So pause the video, and then when you're ready, resume. So now what we'd like to do, and this is continuing on the work that we did earlier, is we want to go ahead and represent this function right here as a step function. So we could represent f of t as, the first thing I want to do is I want to always have the function 2 turned on up until at least 3. So it'll just be the function 2. Then when t is between 3 and 4, I want it to be broadcasting not a 2 any longer, but a minus 4. To make that happen, I'm going to subtract 6 times the step function of t minus 3. If you'd like to pause, at this point, and we're not done with this, but at this point, notice if I were to plug a 0 into this, this would just be 2 minus 6 times the step function of 0 minus 3. And here, remember that the step function outputs a 0 if the argument is negative, and outputs a 1 if the argument is greater than or equal to 0. Since in this case the argument of the step function is negative, it outputs a 0, and so this just outputs a 2, as we expected. But if I were to plug in at this point, if I were to plug in the number 3.5, this would be 2 minus 6 times the step function of 3.5 minus 3. In this case, the argument of the step function is positive, and so it broadcasts a 1. So we get 2 minus 6 times 1, which is equal to negative 4, which is what we want it to output if we have a t value between 3 and 4. So far we're looking pretty good. Let me scoot this over. Then, after t is equal to 4, we want this function to actually broadcast a 1. So we're going to add to this. We're currently at outputting values of negative 4. We want to output 1. So we're going to take something times the step function of t minus 4, where this something turns on a signal at t equals 4 that is going to cause the sum of these two signals plus this signal to output a 1. For that to happen, then, in this case, we have to have it output a 5. Again, it's worth checking that this function still works. If we were to plug in, say, the value of 7 into this function, we want it, based on the description of the piecewise function, to go ahead and output a 1. But we can confirm that, because if we plug a 7 into our step function, this would be 2 minus 6 times the step of 7 minus 3, plus 5 times the step of 7 minus 4. So we get the 2 that's always being broadcasted. We also get the minus 6 that we start broadcasting when t is 3 or greater. And then we get the plus 5 that we start broadcasting. Let me go ahead and put the times 1s in here, folks. So that's times 1 because the step function outputs a 1 there, plus 5 times 1. Again, this is broadcasting a 1 because the argument inside the step function is positive. And in this case, if we sum these all together, we get 7 minus 6, which we do get indeed the 1 that we wanted. So this is our step function for this piecewise function. What I'd like you to do now is I'd like you to go ahead and compute the Laplace transform of the step function. So I'll help you get started. We want to do the Laplace transform of the step function of t minus a, and that's equal to, by definition, the integral from 0 to infinity of the step function times t minus a e to the minus st dt. So folks, if you're having trouble going from this statement to this statement, you really need to come see me. Then here, I'll let you think about this. What you're going to do is you're going to break it up into the pieces. Break up the integral. And if you're stuck, take a look back at number 7 in your in-class notes on the unit step function. to finish that out. So now please pause the video, folks, and calculate the Laplace transform of the unit step function. So folks, your work should show that we end up with e to the minus a t all over s when we do that computation. So now let's go ahead and compute the Laplace transform. Using this information, let's compute the Laplace transform of the step function up above here that I've boxed in green. So if we're going to compute the Laplace transform of that f of t, that's the Laplace transform of 2 minus 6 step t minus 3 plus 5 step t minus 4. And then we remember that the Laplace transform is a linear transformation, so constants factor out, and we can distribute the Laplace transform over sums and differences. The Laplace transform of 2 would just be 2 over s. The minus 6 would factor out of the Laplace transform of the step function t minus 3. And then using this rule up here, oh, folks, this should be a s, not a t. So that should be an s. Watch that, folks. That's a bad mistake. Just as a reminder, we're taking a function from the time domain. We're applying the Laplace transform to it to bring it into the s domain. And so any expression left over in this after the transform should not have the variable t in it. And in fact, that t up there should have been an s. So when I use this rule to help with the computation of the step function of t minus 3, we end up with e to the, careful, watch the signs here, folks, because there's the minus sign in the expression t minus a. So a in this case is understood to be 3, and then we get minus 3s over s. Likewise, again, by the linearity, we get the plus 5, and then when we apply the Laplace transform to the step function of t minus 4, a is being played by 4, so we get e to the minus 4s all over s. So folks, I feel like now is a really good time for a visualization of part of the Laplace transform. This sort of shows the utility of it. This is my personal way of thinking about the Laplace transform. Many piecewise discontinuous functions are smoothed out when transforming the function from the t domain to the s domain. So below here, we've got the graph of f of t, which, surprise, this graph is the same function, piecewise function, that we had here. So hopefully your solution to this was just this statement here. And in the time domain, it's got discontinuities. It's got a discontinuity at time t equals 3, and another discontinuity at time t equals 4. And what I'm saying in this statement, this is how I like to think about the, when we look at the Laplace transform, we have the 0 to infinity f of t e to the minus st dt. And I like to think of this multiplication here as somehow smoothing out the discontinuities of the function in the time domain. Now, this is not a good, realistic representation of what the Laplace transform does. What the author has done here is they're showing there's f of t in the time domain. That's how we're used to representing functions of one variable. But then the author has taken and represented the function f of s, capital F of s, in the s domain here. And that's a little bit misleading. It's not something we're getting into this course, but I think I've highlighted this before, that s is usually a complex number. And graphs of complex numbers do not look like graphs of real-valued functions. And so what I'd like to say is that here we've got the graph of the original function f of t, and this is really just the real part of f of s represented here. But the point still stands where we start off with a function with discontinuities in it. And with the exception of the discontinuity still at 0 in this case, the graph of this function has been smoothed out when we applied the Laplace transform to it. That's part of the reason why we're able to work with these discontinuous forcing functions in the Laplace transform and have everything work out so well. Okay.